Professional diving is diving where the divers are paid for the work. There are several branches of professional diving, the best known of which is probably commercial diving. Any person wishing to become a professional diver normally requires specific training that satisfies any regulatory agencies which have local authority, such as U.S. Occupational Safety and Health Administration, United Kingdom Health and Safety Executive, or South African Department of Labour. Due to the dangerous nature of some professional diving operations, specialized equipment such as an on-site hyperbaric chamber and diver-to-surface communication system is often required by law. Procedural aspects. The primary distinction between professional and recreational diving is that the recreational diver is responsible primarily for his/her own actions and safety, but may voluntarily accept limited responsibility for dive buddies, whereas the professional diver is part of a team of people with extensive responsibilities and obligations to each other and usually to an employer or client, and these responsibilities and obligations are formally defined in legislation, regulations, operations manuals, standing orders and compulsory or voluntary codes of practice. In many cases, a statutory national occupational health and safety legislation constrains their activities. Branches of professional diving. Commercial diving. Offshore diving. Offshore diving is the most well-known branch of commercial diving, with divers working in support of the exploration and production sector of the oil and gas industry in places such as the Gulf of Mexico in the United States, the North Sea in the United Kingdom, and Norway, and along the coast of Brazil. The work in this area of the industry includes maintenance of oil platforms and the building of underwater structures used in the production process. Equipment used for offshore diving tends to be surface-supplied equipment, but this does vary depending on the nature of the work and location. For instance, Gulf of Mexico-based divers may use wetsuits, whilst North Sea divers need dry suits or even hot water suits due to the temperature of the water. Inland. Onshore diving. Inland or onshore diving is very similar to offshore diving in terms of the nature of work and the equipment used, the work often being in support of land-based civil engineering projects, with the majority of the work either underwater survey or engineering work. The types of dive sites this covers is varied, however, and divers can be found working in harbors and lakes, on hydroelectric dams, in rivers and around bridges and pontoons, with the bulk of this work being undertaken in freshwater. They are often required to inspect and repair outfalls which require at times up to 600 feet, plus penetrations, which require a multitude of safety requirements. Onshore divers typically can be at home every night and earn more per hour than their colleagues who work offshore. However, depth pay and minimum 12-hour shifts offshore must be taken into consideration. The equipment used does depend on the nature of the work and location, but normally a mixture of scuba and surface-supplied diving equipment is used by divers and their employers. Hazmat diving. Hazmat diving is one of the most dangerous branches of the commercial diving industry, employing highly skilled and experienced staff. Typical work involves diving into raw sewage or dangerous chemicals, such as paper pulp, liquid cement, or oil sludge. This leads to special requirements. The divers need to be vaccinated against diseases such as hepatitis and tetanus. Suitable equipment and competent personnel are required for decontamination of the diver and diving equipment after a dive. Emergency procedures must be planned and equipment and personnel in place to safely recover the diver if something goes wrong. The tasks a diver may be required to do in a contaminated environment include essential maintenance of underwater valves and sluice gates, repairing damaged pipelines, Pollution control work to contain, control and clean up after a pollution incident. Sampling activities, such as those performed by United States Environmental Protection Agency, units specializing in polluted water diving, such as Region 10 and the Environmental Response Team dive units. Diving in landfill sites to maintain the pumping equipment, vital in preventing landfill sites from filling up with rainwater and contaminating the water table. Welding inside functioning sewers or working in septic tanks. Miscellaneous repairs and finding lost objects. Finding bodies. Sewer diving is one of the most dangerous of all the hazmat jobs due to the disease vectors carried by raw sewage and because hypodermic needles and broken glass may contaminate the raw sewage, creating risks of contracting diseases through cuts and punctures. Divers working in a dangerously contaminated environment wear a full dry suit with integral boots. Cut-resistant dry gloves and helmet will seal directly to the dry suit, leaving no skin exposed to the environment. The diver will generally use a free-flow diving helmet which continually supplies more air than the diver needs to breathe so that there is a constant outflow through the exhaust valve, as the internal pressure must be slightly higher than ambient to maintain the flow. A free-flow helmet has a significantly lower risk of leakage back through the exhaust valve compared to a standard demand helmet where the exhaust valve must maintain a watertight seal against a slightly higher external pressure during inhalation. The risk of leakage through the exhaust valve of a demand system can be reduced in three ways. A series system of valves can be used. The exhaust gases must pass through two sets of exhaust valves before reaching the contaminated environment, and therefore contaminated water would have to leak back through both sets of valves to get to the diver. Positive pressure systems maintain a slightly higher pressure inside the mask or helmet than the ambient pressure on the outside, ensuring that any leaks flow from inside to outside. And reclaim type systems duct the exhaled breathing gas back to the control panel on the surface, but do not necessarily reclaim the exhaust gas. Combinations of these methods are possible depending on the assessed risk. The dry suit will be made from a material resistant to the hazardous materials at the site. Normally the diver wears a vulcanized rubber dry suit, which is relatively easy to decontaminate as it has a slick outer surface, but occasionally a neoprene or tri-laminate suit is needed. Often, a diver will wear extra protection over the dry suit to reduce the risk of a puncture. Leather, PVC and nylon coveralls are used for this purpose. In such diving, light levels are often very low and the water is usually very turbid, so divers may rely on touch to guide them, and they are connected via the umbilical to the surface. The umbilical serves as a supply of breathing gas for communications, and as a lifeline to find and retrieve the diver in an emergency. It is also used as a guide to find the way back to the surface. Nuclear diving. Nuclear diving is similar to hazmat diving. The difference is the exposure to radiation instead of the waterborne contaminant. To this end, different precautions are required for nuclear diving, mainly equipment which will not absorb radioactive contamination and pose a disposal problem after several dives. Moreover, exhaustive briefing of the grouper diver for the specific environment he is going to work, depth, water temperature and potential radioactive sources. Heat stress can also be a danger for the diver, in which case a cold water suit may be used. The cold water suit is a special canvas coverall which floods the outside of the diver's dry suit with chilled water, countering the dangerously high ambient water temperature. A dosimeter is used to ensure that the diver does not receive a dangerous dose of radiation during the dive. assisting in calculating the maximum length of the dive. In addition, the dosimeter can also be used to find radiation hotspots, which can indicate areas in need of repair. Scientific diving. Scientific diving is the use of diving techniques by scientists to study underwater what would normally be studied by scientists on land. Scientific divers are normally qualified scientists first and divers second, who use diving equipment and techniques as the way to get to the location of the fieldwork. The direct observation and manipulation of marine habitats afforded to scuba-equipped scientists have transformed the marine sciences generally, and marine biology and marine chemistry in particular. Underwater archaeology and geology are other examples of sciences pursued underwater. Some scientific diving is carried out by universities in support of undergraduate or postgraduate research programs. Government bodies such as the United States Environmental Protection Agency and the UK Environment Agency carry out scientific diving to recover samples of water, marine organisms and sea, lake or riverbed material to examine for signs of pollution. Equipment used varies widely in this field, but surface-supplied equipment, though quite uncommon in the UK, is growing in popularity in the US. The short number of dives made by scientific divers in normally quite shallow water, and the UK governmental regulations that make surface-supplied equipment cumbersome, when combined with a need for easy transportation, make surface-supplied gear uneconomic and undesirable for UK scientists to use. Scientific diving organizations include the American Academy of Underwater Sciences, the European Scientific Diving Panel, the German Academy of Underwater Sciences. The two standard references for scientific diving operations are Scientific Committee of CMAS Fleming, and CINAMP Max MD Code of Practice for Scientific Diving, Principles for the Safe Practice of Scientific Diving in Different Environments. UNESCO Technical Papers in Marine Science 53, United Nations Educational, Scientific and Cultural Organization (DIV) of Marine Sciences, Paris, ISSN 0503-4299, OCLC 18056894. Joyner James T. NOAA Diving Manual, Diving for Science and Technology, 4th edition, 2001, U.S. Department of Commerce, National Technical Information Service, Australia. Although the first scientific diving expedition in Australia was carried out by Sir Maurice Young to the Great Barrier Reef in 1928, most scientific diving did not start until 1952, when the Commonwealth Scientific and Industrial Research Organisation began work to understand the pearl beds of northern Australia in 1957. Commercial divers worked under Australian standard CZ-18 work in compressed air in 1972. This standard applied to caisson workers and divers, so the underwater work was drafted into as 2,299 underwater air breathing operations in 1979. In 1987, a rewrite of AS 2299 included scientific diving in the regulations, even though the divers had been self-regulating under the Australian Marine Sciences Association. At the time, the AMSA and the Australian Institute for Maritime Archaeology began a collaboration to draft a new standard for scientific diving. South Africa. In South Africa, scientific diving is considered a form of commercial diving and is within the scope of the Diving Regulations 2009 and the Code of Practice for Scientific diving approved by the Chief Inspector of the Department of Labor. Under Drive 2009, the codes of practice are guidance and not compulsory practice. They are provided as recommended good practice, and in theory need not be followed providing an acceptable level of safety is achieved in terms of the Occupational Health and Safety Act No. 85 of 1993. However, in this case the onus is on the diving contractor to ensure acceptable safety during the diving operation. The level of safety required is specified in the OS Act as reasonably practicable, taking into account a number of factors, including cost-effectiveness, availability of technology for mitigation and available knowledge of hazards. Use of the relatively flexible scientific code is restricted to clients which are registered as organizations engaged in either scientific research or higher education. United States. In the United States, scientific diving is permitted by the Occupational Safety and Health Administration to operate under an alternative consensual standard of practice that is maintained by the American Academy of Underwater Sciences. The perspectives on the regulation of scientific diving of two diving safety officers and founders of the American Academy of Underwater Sciences, Lloyd Austin and Philip Sharkey, can be found in Oceans Volume 15, pp. 460 to 463. To be able to avail itself of the scientific diving exemption, the institution under whose auspices the work is carried out must meet 4 tests. The Diving Control Board, consisting of a majority of active scientific divers, must have autonomous and absolute authority over the scientific diving program's operations. The purpose of all projects using scientific diving is the advancement of science. Therefore, information and data resulting from the project are non-proprietary. The tasks of a scientific diver are those of an observer and data gatherer. Construction and troubleshooting tasks traditionally associated with commercial diving are not included within scientific diving. Scientific divers, based on the nature of their activities, must use scientific expertise in studying the underwater environment and, therefore, are scientists or scientists in training. Media diving. Media diving is a term used to describe divers engaged in underwater photography and underwater cinematography outside of normal, recreational interests. Media diving is often carried out in support of television documentaries, such as the BBC series Planet Earth or Hollywood blockbusters, with feature films such as Titanic and The Perfect Storm featuring underwater photography or footage. Media divers are normally highly trained camera operators who use diving as a method to reach the workplace, although some underwater photographers may start as recreational divers and move on to make a living from the hobby. Equipment in this field is varied, with scuba and surface-supplied equipment used, depending on requirements, but rebreathers are often used for wildlife-related work as they are normally quiet, release few or no bubbles and allow the diver a lengthy bottom time with a reduced risk of frightening off the subject at hand. Military and naval diving. Military diving covers all types of diving carried out by military personnel. There are a number of different specializations for a military diver to choose. Some depend on which branch of the military they have joined or where the military needs more divers. Typical offensive activities include underwater demolition, infiltration and sabotage. This being the type of work elite regiments such as the UK Special Boats Service of the USA Navy SEALs carry out. Defensive activities are centered around countering the threat of enemy special forces and enemy anti-shipping measures, and typically involve defusing mines, searching for explosives, explosive devices attached to the hulls of ships, and locating enemy frogmen in the water. Military divers need equipment which hides the position and prevents explosives from being set off, and to this end, they use rebreathers which produce less noise due to bubbles emitted from the equipment, and few or no bubbles on the surface, and which contain no magnetic components. This continues down to the design of the diving suit, which will normally have a non-magnetic zipper, and the face mask may be fitted with special anti-reflective glass. Some navies have gone further and given the divers special contact lenses instead of large face masks to cut down on the risk of a reflection. Naval diving is the military term for commercial diving, and is drastically different from military diving. Naval divers work to support maintenance and repair operations on ships and military installations. Their equipment is derived from commercially available equipment, with the U.S. Navy using versions of the Kirby-Morgan helmets and full face masks amongst other equipment. Typical tasks include boat and ship inspection, cleaning and maintenance, demolition of shipwreck and unexploded ordnance, ship, submarine, downed aircraft, and other military hardware salvage or recovery. Underwater mine clearance, investigating unidentified submerged divers. The United States Army has its own organic assets. These are the Army Engineer Divers. Experimental diving is conducted by the U.S. Navy's Experimental Diving Unit and involves meeting military needs through the research and development of diving practices and diving equipment, testing new types of equipment and finding new and safer ways to perform dives and related activities. The USNEDU was responsible for much of the early experimental diving work to calculate decompression tables and has since worked on such developments as heated diving suits powered by radioactive isotopes and mixed gas diving equipment, while the British equivalent perfected the Mark Chapter 10 submarine escape suits utilized by both the Royal Navy and the U.S. Navy. Police divers are normally police officers who have been trained in the use of diving techniques to recover evidence and occasionally bodies from rivers, canals and the sea. They may also be employed in searching shipping for contraband substances fitted to the outside of hulls to avoid detection. The equipment they use depends on requirements, but the requirement for communications at some sites does often require the use of full face masks with communication equipment, either with scuba or surface-supplied equipment. Diving instructors. Instructors for each of the above modes of diving are highly qualified individuals operating under the auspices of a governmental agency. Standards for instruction are authorized by agencies to ensure safety. Recreational dive instructors differ from other types of professional divers as they normally don't require professional level qualification, but a relevant recreational qualification from a recognized training agency such as GU, SDI, TDI, NAUI, PADI, SSI, and EABSAC, which permits them to teach. Dive instructors teach a wide variety of skills from entry-level diver training for beginners, to diver rescue for intermediate-level divers and technical diving for more experienced divers. They often operate from dedicated dive centers at coastal sites or through hotels in popular holiday resorts or simply from a local swimming pools. Initial training is carried out mainly on conventional scuba equipment, but with the increasing use of rebreathers, the use is also taught. Not all dive instructors are professionals. Many instructors are amateurs with careers outside the diving industry. Commercial diving instructors normally require professional diving qualifications. They typically teach trainee commercial divers how to operate types of diving equipment and typical underwater tools they will use in the course of the work. Commercial diving instructors will use similar equipment to commercial divers in the course of the work. Aquarium diving. Aquarium divers normally hold some form of professional qualification, either as a diving instructor or in the UK a House Part 4 qualification. The larger aquariums can have considerable size and depth, in the UK 35 by 25 meters and 5 meters deep with 3.8 million liters of water. The jobs are varied but are centered around the maintenance of the tank and livestock and public entertainment. They include feeding of the livestock, tank cleaning, shows, taking members of the public into the tank, equipment, diving suit. Depending on the water temperature, depth and duration of the planned dive, the diver will either use a wetsuit, dry suit or hot water suit. A wetsuit provides thermal insulation by layers of foam neoprene, but the diver gets wet. Hot water diving suits are similar to a wetsuit but are flooded with warm water from a surface water heater that is then pumped to the diver via an umbilical. A dry suit is another method of insulation, operating by keeping the diver dry under the suit, and relies on either the suit material or the air trapped in thermal undergarments to insulate the diver, and also provides better isolation from environmental contamination. Certain applications require a specific type of dive suit. Long dives into deep, cold water normally require a hot water suit or dry suit, whilst diving into potentially contaminated environments requires a dry suit, dry hood, and dry gloves at a minimum, thereby keeping the diver completely isolated from the diving environment. Breathing apparatus. A number of factors dictate the type of breathing apparatus used by the diver. Typical considerations include the length of the dive, water contamination, space constraints and vehicle access for support vehicles. Some disciplines will very rarely use surface-supplied diving, such as scientific divers or military clearance divers, whilst commercial divers will rarely use scuba equipment. Scuba diving. Scuba equipment is not commonly used in civilian commercial diving, but is often employed by scientific, media and military divers, sometimes as specialized equipment such as rebreathers, which are closed-circuit scuba equipment that recycles breathing gas instead of releasing it into the water. It is the rebreathing of gas that makes rebreathers ideal for long-duration dives, efficient decompression when the gas mix is adjustable, and for the observation of animals in the wild due to the lack of noisy bubbles. These characteristics also make rebreathers ideal for military use, such as when military divers are engaged in covert action or when performing mine clearance where bubbles could potentially set off an explosion. Open-circuit scuba equipments are occasionally used by commercial divers working on sites where surface-supplied equipment is unsuitable, such as around raised structures like a water tower, or in remote locations where it is necessary to carry equipment to the dive site. Normally, for comfort and for practicality, a full face mask such as those manufactured by Kirby Morgan will be used to allow torches and video cameras to be mounted onto the mask. The benefit of full face masks is that they can normally be used with surface-supplied equipment as well, removing the need for the diver or the company to have two sets of expensive equipment. Surface-supplied diving. This is perhaps the most common type of equipment used in professional diving, and the one most recognized by the public, made familiar through films such as The Abyss. Surface-supplied equipment can be used with full face masks or diving helmets. Helmets are normally to be found fitted with diver-to-surface communication equipment, and often with light sources and video equipment. The decision between wearing a full face mask or a full diving helmet comes down to job requirements and personal preference. However, the impact protection and warmth offered by a full diving helmet makes it popular for underwater construction sites and cold water work. Breathing gas for the diver is piped down from the surface through a long, flexible hose, called an umbilical. In addition to breathing gas, the umbilical may have additional hoses and cables for such things as communications equipment, a pneumofathometer for measuring depth, or hot water should the diver be using a hot water suit. The umbilical must be strong enough to support the diver's weight, with a significant safety margin, because it may be used by surface personnel to pull the diver out of the water. The diver's breathing gas is pumped down from either high-pressure tanks or through a gas compressor. Saturation diving. If the diver is to be working at extreme depths for a long period, the diver may live in a special underwater habitat called a diving chamber or a pressurized surface habitat called the saturation system. This type of surface-supplied diving is known as saturation diving. The same technique for supplying breathing gas as regular surface-supplied diving is used, with the diving bell receiving breathing gas and electricity from a diving support vessel on the surface. Due to the often extreme depths the diver is working at, specialized helium-based breathing gas mixtures are often used to prevent both nitrogen narcosis and oxygen toxicity which occurs at these extreme depths.